Hi, we're CRATER, Caltech's first ever collegiate rover team. Over the last 6 months, our undergraduate team of 15 students has been hard at work designing, building, and testing ERNIE, our experimental rover for navigating extreme environments. We hope to continue building and developing our rover on the road to CIRC at the end of this summer. To tackle such a complex interdisciplinary project, we split up into sub-teams centered around the different rover subsystems: chassis drive, manipulator, electrical, communications, software, and science.
The CRATER drive and chassis subteam's main objective was to design, manufacture, and test a robust mechanical design capable of reliable performance across a wide variety of terrains. To that end, the tried and true rocker bogie system was selected due to its low mass and complexity, increased stability across extreme terrains, and flight heritage. Our particular implementation further prioritizes reducing system mass and complexity, being primarily constructed out of hollow aluminum 6061 tubing and plates. Finally, with no permanent welds or rivets, our rover is simple to disassemble, maintain, and augment with new hardware and novel capabilities, a flexibility in design that CRATER intends to explore further during future testing. In fact, our upcoming revision places our motors higher on the suspension legs so as to increase the rover's clearance and protect the motors during operation. The drivetrain consists of a low-mass roller chain transmission. 24-centimeter wheelies inflatable balloon wheels with custom hubs provide traction even in sandy environments and cushioning while traversing rough, rocky terrain. The differential bar inverts the rotation of one rocker and transfers it to the opposite rocker, increasing stability and allowing for the rover to scale obstacles of a height twice its wheel diameter. Coupled with its robust Maxon brushless DC motors, our rover's mechanical design is optimized to power through and over even the most locomotion-impeding obstacles, and provide a dependable platform upon which the other rover subsystems can confidently build off of.
The manipulator subsystem is designed to have fine positional and rotational control in task space, while providing the capability to lift large loads of up to 5 kilograms. To maximize the reachable task space, a 6-degree freedom design was chosen, which provides full 6-dimensional control. At the tip of this assembly is a 2-degree freedom end effector, which enables grasping and interacting with objects. The 6-off arm is designed to meet control requirements for the overall subsystem while minimizing mass and cost. All joints have custom gearboxes to meet torque requirements, and all motors implement sensored field-oriented control with additional encoders on the joint output shafts to enable position, velocity, and torque mode controls of the joints. The end effector features servos with torque mode control, allowing the gripper to impart controllable forces on held objects. This enables delicate manipulation of items such as switches, knobs, and other potentially fragile items. The gripper also features a worm gear stage, eliminating the need for large currents at the end effector when gripping heavy objects. The subsystem team has made significant progress towards assembling and testing a competition-ready arm. All joint gearboxes are entering assembly, with the motor drives and circuitry for these assemblies implemented and tested. Furthermore, the end effector has been fabricated and is currently in acceptance testing. Current efforts are on fabricating joint gearboxes and integrating joint assemblies, putting us on a good pace to deliver a competition-ready arm for the rover by the end of June.
The electrical system on the rover is designed with efficiency, robustness, and safety in mind. The system is powered off 3 7S LiPo batteries connected in parallel to provide roughly 25 volts with 24 amp hours. This ensures a runtime well over 30 minutes, even when transients are being drawn by the motors. We have a contingency plan for any disruption to the batteries. Through either the physical press of a button or through a remote command, we can control relays to disconnect batteries from all loads. Fuses are also included throughout the system to protect each load. Fuses are placed on the output of batteries, as well as the input and output of each DC-DC converter. Further battery protection includes a battery management system, or BMS. This BMS includes active balancing of cells, over and under current protection, as well as over and under voltage protection. Before the rover drives, we can set values for each of these protections via Bluetooth, and we can manually control discharge behaviors. While the rover is driving, we can communicate to the VMS via RS485 to UART converter to the Arduino for receiving data on the cells. The rover communicates with the base station over both a 2.4 GHz Wi-Fi link and a 900 MHz long-range radio. The Wi-Fi link is used for transmitting videos while the rover is in a close proximity. This frequency is implemented using a Ubiquiti Rocket M2 with a 120-degree sector antenna at the base station and an omnidirectional antenna at the rover. The 900 MHz frequency is for sending drive commands, remotely disabling the drive system, and receiving data from the rover, such as battery cell health. For this frequency, we use an Adafruit Feather with a low-raw chip. We've conducted testing on campus to ensure integrity of the signal across varying distances and through varying obstacles.
Our software architecture is primarily built on the robot operating system, ROS. For motor control, we utilize an Arduino Mega connected to all of the motors, which communicates over serial with a Jetson or a Nano, acting as the central processor for the rover. We also connect an Intel RealSense D455 camera to the Nano, providing a depth representation of the terrain ahead of the rover. For autonomous navigation, we utilize this point cloud data along with the 6-axis IMU and GPS module. Using the point cloud, we are able to map out the surroundings of the rover as we drive, giving a pose estimation within the global map. This estimate is made more accurate by data from the IMU, allowing us to simultaneously map the environment and know the rover's position in it. Using the GPS module, we are able to direct the rover's motion on a higher level towards the GPS coordinates of interest. For identifying signs of life in soil samples, we decided to primarily focus on the presence of carbohydrates and proteins within the samples. We sampled soil using a swappable scooper attachment on the manipulator arm end effector. For detecting extant life, we decided to use the Bradford protein assay, while for extinct life, we decided on Benedict's reagent test for carbohydrates. Since these are both indicator tests, we use a carousel of cuvettes built to function as a custom spectrophotometer, measuring the absorbance of the samples. For rock sampling, we have an ESP-I microcontroller which is placed at the end of the arm, allowing us to send image data back to the base station for processing, as well as to run a computer vision model on board to determine the type of rock sampled, as this could be indicative of extinct life. Thanks for watching. Really proud of the effort that we put in over the past 6 months to get this rover working, and we thank you for your consideration.